Hi everyone. So first of all, I would like to thank the organizers for the invitation. Okay, so as the title suggests that today I am going to talk about knots and links in over-twisted manifolds. And this will be a two-part talk. In the first part, I am going to talk about the motivation, why one should care about these knots, some background material, which I'll keep less technical, and some history. The second part will involve my recent results about classification of loose links, an invariant of links, and then some future work. Okay, so let's start with part one. In three-dimensional contact geometry, we have a very nice dichotomy, which is tight versus over-twisted. I will define this later. So if you look at this literature, you'll see that tight contact structures grab a lot of attention. Tight contact structures are rare, and the classification of tight contact structure is a very difficult and interesting problem in contact geometry. So the natural question that arises that what about over-twisted contact structures? Now here comes Eliashberg's classification. So Eliashberg in '89 proved this very nice and important result, which tells us that over-twisted contact structures up to isotopy are in one-to-one correspondence with two plane fields up to homotopy. So if we understand the homotopy class of two plane fields, we understand over-twisted contact structures. The next result is by Gompf, and he tells us that D2 and D3 invariant completely determines two plane fields, again up to homotopy. Okay, what are D2 and D3? D2 and D3 are obstruction classes. So very vaguely speaking, they measures how the two plane fields are different on the two skeleton and the three skeleton of the manifold. So for example, let us take S3. Now S3 doesn't have any two skeleton, that's why S3 doesn't have any D2, but D3 determines all the two plane fields on S3 up to homotopy. Okay, now if we combine Eliashberg and Gompf's result, together these tell us that D2, D3 determines over-twisted contact structures up to isotopy. So we have a complete classification of over-twisted contact structures. Now, due to this classification, what happened is the knot theory associated to over-twisted contact structures became less explored. So recently, mathematicians started working on this, and they are finding lots of interesting results. And also, it turns out that the knots in over-twisted contact structures are very different than knots in tight contact structures. So in this talk, I'm going to talk about these knots. Okay. So let us talk about some background now. A contact structure on a three manifold is a nowhere integrable two plane field. Now, what is this condition nowhere integrable means that if we can never find a surface in the manifold where the contact planes will be tangents everywhere. Basically, this tells us that contact planes are twisting. Here is an example. This is the standard R3. So R3 with the standard contact structure, which is defined as a kernel of a one form. I did not mention it before, but contact structure can be defined as a kernel of a one form. And here the one form is dz minus y dx. And here is this picture, which, as you can see, that this contact planes twist and they take a left-handed twist. And this is actually a tight contact structure, like before I mentioned. Now, what is an over-twisted contact manifold? This talk is on over-twisted manifolds, so I should define it first. Contact-free manifold is over-twisted if there is an over-twisted disk embedded in it. And here is a picture of an over-twisted disk. Now, if you look at this picture, along the boundary, the contact planes are all tangents, and this is the definition of an over-twisted disk. So if you find such a disk in the manifold embedded, that's important, then it will be over-twisted. And if there is no such disk, then the manifold is tight. All right. Next, knots in contact manifolds. There are two types of knots in a contact manifold. They are known as Legendrian and transverse. And on the left-hand side, we have a local picture of a Legendrian knot. So if we draw a tangent vector, pick any point on the knot and draw the tangent, it must lie on the contact plane. That is the definition of a Legendrian knot. For transverse knot, pick any point and draw a tangent vector that is transverse to the contact plane. So these are the local pictures, and here are the definitions. Okay, now classical invariants. There are two types of classical invariants for a Legendrian knot. They are Thurston-Bannequin invariant, which is known as TB, and then rotation number, which is known as rot. On the other hand, transverse knots, they have just one classical invariant, which is known as the self-linking number. Because I promised that I will not go into technical details, these all invariants are well defined for null homologous knots. That's all I will say about these. All right. But yeah, of course, you can ask me that what about non-null homologous knots? They are relative versions of these invariants. But for the purpose of this talk, we don't need them. All right. Now, is there any relationship between Legendrian and transverse knot? This is a very, very important tool in contact geometry. I should not say tool, but an important technique in contact geometry, which allows us to move back and forth between Legendrian and transverse representative of the same knot type. Now, from Legendrian to transverse, we use transverse push-offs. And this operation is unique. On the other hand, if we have a transverse knot, we can apply Legendrian approximation, which will give us our Legendrian knot. But unfortunately, this Legendrian approximation operation is not well defined. So for the same transverse knot, we can have lots of Legendrian approximation. But again, there's a good news, and that any two Legendrian approximation are related by something known as negative stabilization. Now, negative stabilization is a local operation on a Legendrian knot. Okay. Now, what about knots in over-twisted manifolds? So there are two types of knots in an over-twisted manifolds. They are known as loose and non-loose. Now, why there are two types of knots? Uh, let us take this example. Suppose we are in an over-twisted manifold and we have a knot and we remove the tubular neighborhood of the knot. Now, what can happen? Either the complement becomes over twisted, it's still over twisted, or it can become tight. These two things can happen. And how it can happen is if the knot intersects every over twisted disc in the manifold, then by removing the tubular neighborhood of the knot, I'm also getting rid of the over twisted discs. So the manifold becomes tight. So that's why there are two types of knots. So non-loose are those knots with complement tight, and loose knots complement over twisted. There are lots of ways to define these two knots. One is this, that the complement is tight versus complement over twisted. We can also say that a non-loose knot is such a knot which intersects every over twisted disc in the manifold. Loose knot is if there is an over twisted disc disjoint from the knot. So there are a lot of ways to think about. There are also surgery definitions, like if you take a knot and do a surgery on that knot, and if that produces a tight manifold, then it will be non-loose. So a lot of ways to think about these knots. Okay. Now, how these knots are different. Like I mentioned in the first slide, that the knots in over twisted manifolds are different from knots in tight manifolds. Now, how they are different. The first point is the diagram. A knot theorists care about diagrams a lot, like how to draw the knots. So in tight S3, we have a nice way to draw any Legendrian representative of a knot, which is known as front diagram. So I will draw the trivial knot here. So we have our trivial knot, and the front diagram for this is just adding cusps at vertical tangencies. This is how we do it. So, and there is no crossing for this knot, so we do not have to worry about those crossings. But if I want to draw in over twisted, so front diagram, which is this adding cusps, this works in S3 Z standard, which is the tight contact structure. So what about over twisted? We do not have front diagram in over twisted contact structures. So to draw in an over twisted S3, mathematicians come up with a nice diagram, nice way to draw that, which is known as a contact surgery diagram. And this is how we draw it. So a contact surgery diagram is basically a surgery diagram. And this is the surgery picture. This is a +1, +1. And the red component is the unknot. So you just have to do some Kirby moves to check that that's an unknot. And this is in fact a non-loose unknot. And also computing the D3, which is, there are algorithms to compute D3 from a contact surgery diagram. You can find that this invariant is -1. So as I mentioned before, S3 doesn't have D2, only D3, and -1 is the D3. Okay. By now you should notice this thing that drawing a contact surgery diagram is not so easy. For like unknot, it is 3 component, but as soon as we move to trefoil, the contact surgery diagram, I think it has 6 components. So it becomes complicated in over twisted. Okay. Next is existence. Um, first of all, there actually in every contact manifold, we can find a non-loose knot, but we do not know if every knot type has a non-loose representative. So that's a open question. If in S3, every knot has a non-loose representative, we don't know yet. And also one thing is non-loose knots are rare. And this should not be surprising because non-loose knots are very closely related to tight contact structures, right? And tight contact structures are rare. So non-loose knots should be rare as well. Here, I want to mention an interesting fact. And this is due to Eliashberg-Fraser, where they proved that S3Z negative 1 only contains non-loose unknots. That means that if you are in any other over-twisted contact structure on S3 and you find an unknot, that has to be loose. This is very interesting. So this is due to Eliashberg-Fraser. Okay. The next is classification. So there are two types of classification in contact geometry. Actually, there are three types, but two of them are equivalent. So Legendre anisotropy versus contactomorphism. Now, in S3 standard, which is the tight contact structure, these two notions are the same. They are equivalent. So if you can prove up to contactomorphism, that implies up to Legendre anisotropy. But that is not true for any general contact manifold or even in S3 when S3 is over-twisted. So if we can prove something up to contactomorphism, that does not imply Legendre anisotropy. Legendre anisotropy is a lot stronger there. And here there is another notion in over-twisted. So this notion is for over-twisted, which is coarse equivalence. So we say that two knots are coarsely equivalent if we can find a contactomorphism which takes one knot to the other, which is isotopic to the identity. And we will use this notion of equivalence. Okay. Next, some brief history. Let's see what we know about these knots and links. So first of all, these non-loose knots are links, and all the classifications here will be coarse equivalence, not up to Legendre anisotropy. So the first result is about unknot. The unknot is classified by Eliashberg-Fraser in 2000. The next one is negative torus knot. This is due to Geiges-Onaran and later Matkovic. She extended their result, but this is not complete classification. This is partial classification. And this result actually Geiges-Onaran, this was in 2018. Positive torus knots, again by Geiges-Onaran, and this is also partial. And this is also in 2018, in the same paper. Next is Hofflink. This was also by Geiges-Onaran, and this is in 2020. So as you can see that these all classifications of this torus knots are Hofflink, pretty recent. So what about loose knots? The loose knots are those knots with complement over-twisted. Here the up to contactomorphism or up to coarse equivalence classification, this is due to Etnayer. So Etnayer proved that null homologous loose knots can be classified completely by their classical invariance, which is TB and rotation number is enough to classify those knots with over-twisted complements. And in 2019, Khan and Chernov has this result, which is up to Legendre anisotropy, which is stronger, Legendre or transverse isotopy for transverse knots. They classified the knots, but here notice there is a stronger condition. And this is that there is a over-twisted disjoint from both of them. So this is very strong. We need to have a common over-twisted disc in the complement. So let us just compare these two results. The second one is definitely a stronger classification because this is up to isotopy. First one is up to contactomorphism. But then the second one has this strong condition that we need a common over-twisted disc in the complement of both the knots, which is not required for the first result. So we would really like to have a result where we can prove isotopy, classification up to isotopy, when we do not need this condition, the common over-twisted disc, but that seems like a difficult problem. Okay. So the next question is, what about links? What about loose links? If we increase the number of components, what happens with the classification? And that is what I'm going to talk about in the second part of this talk. So thanks for listening.